In astrobiology, we frequently hear the term habitability. People talk about planets being habitable. People talk about planets orbiting distant stars potentially being habitable. What does this really mean? Let's take a brief look at this word habitability. First of all, what makes a planet habitable? We've learned something about the requirements for life. And given those requirements, we can define some criteria that might make a planet habitable. For instance, we would expect a habitable planet to have a source of liquid water, at least as far as we know concerning the requirements of life. Life needs liquid water as a solvent for biochemistry. We also need a planet where there's a source of energy, energy for life to harness in order to carry out its particular biochemical functions. We also need a planet where there's a source of elements and other nutrients to sustain life. And finally, of course, we need physical conditions that are suitable to life, physical conditions that are within the boundaries for life to be able to persist on a planetary surface. One of the most enduring concepts in astrobiology is the habitable zone. This is the zone around a star where conditions are suitable for liquid water to form on the surface of a planet. This is just an image depicting the habitable zone in our own solar system that lies between Venus and Mars. And of course our own planet, planet Earth, is within the habitable zone, allowing bodies of liquid water to persist on the surface of our planet. It's that zone where the solar heating, perhaps combined with the greenhouse effect of a planet, is sufficient to create bodies of liquid water on the surface of a planet. The habitable zone is a very useful concept because we can use it to assess the habitability, for example, of planets orbiting other stars and to see where in the star system that planet resides and whether it is far enough away from the sun not to be too hot, but close enough to have liquid water on its surface and for that liquid water not to freeze. The habitable zone, of course, will vary depending upon the star. For very hot stars that give out more energy, the habitable zone will be further away. And for very cool stars, the habitable zone will be much further in, much closer into the star. And so the habitable zone will vary depending upon the temperature and, of course, on the age of the star. One has to be a little careful with this concept of the habitable zone because liquid water can exist outside the habitable zone in particular environments. This is the moon of Jupiter, Europa, about the same size as our own moon. And it has an icy surface, a crust of ice, under which there seems to be a liquid water ocean. How does that liquid water ocean get there when it's far outside the habitable zone, very far away from the star, where it's very cold in the outer solar system? Well, this liquid water ocean seems to be formed by tidal buckling. The huge gravitational force of Jupiter buckles Europa and creates heat in the center of that moon that melts the ice and creates a liquid water ocean. So here's an example of a moon that seems to have liquid water despite the fact that it's outside of the classical habitable zone. But nevertheless, that doesn't detract from the fact that the habitable zone is still a useful concept in astrobiology. We just have to be careful about the way we use it and the possible exceptions. There are other things that people have discussed that are required for habitability, and one of them is active geochemical turnover. If a planet's not geologically active, eventually nutrients and energy sources will be used up for life and the planet will essentially run down. There'll be no new energy supplies, no new nutrients. We need active geochemical turnover, first of all to recycle elements and nutrients in the crust that are needed by life, but also to generate chemical reactions that can create new sources of energy, chemical disequilibria that's necessary for life to harness those energy supplies to grow. There are a couple of ways in which that might happen. We might have, for example, plate tectonics, where one plate subducts under another plate and becomes heated and melts. And these movements of plates over the surface of a planet within its crust create this turnover that's necessary to create the elements and nutrients for life. Another way is active volcanism. Volcanoes spewing lava and magma onto the surface of a planet that also creates turnover within the crust and generates new energy and nutrient supplies for life. Of course, it's also important that the physical conditions are not too extreme for life for long periods of time. It's no good having a planet where conditions are suitable for life for a short period and then it becomes too extreme and then suitable again. We need conditions for life that persist possibly over billions of years. And this leads to another concept called the continuously habitable zone. The continuously habitable zone is that zone around a star where not only is there liquid water, but there are conditions suitable for life for many billions of years to allow life to evolve and to proliferate and maybe to eventually evolve into multicellular life and intelligence. So we need conditions that are suitable for life for billions of years. People have also speculated on other requirements for habitability. For example, some people think that a moon is very important for a planet to be habitable. In our own case, our own moon is responsible for stabilizing the tilt of our planet, or the obliquity. If we didn't have a moon, the tilt of our planet would vary wildly over tens of thousands of years, and this would change the climate very dramatically over relatively short periods, at least geologically speaking. Some people say that if we had no moon, the climate would vary so wildly, it would really be difficult for life to become sustained on the planetary surface. But we have to be careful about these sorts of assumptions. One could argue, for example, that if we didn't have a moon and the climate varied wildly, it would lead to a biosphere full of organisms that were very good at dealing with rapid climatic changes. Maybe such rapid climatic changes would make them better at evolving to deal with catastrophic changes, such as asteroid or comet impacts or giant volcanic eruptions, perhaps being a generalist organism that could survive wildly varying climatic conditions would be good for life over long periods of time. So you can see that there are controversies and complications in really finding out what the true criteria for habitability are, what is really needed on the surface of a planet for life to be able to persist. What have we learned in this lecture? Well, we've learned that the habitable zone is a zone around a star where liquid water is stable on a planetary surface. We've learned that the habitable zone will of course vary according to the temperature of the star, and although it's a useful concept, water can exist outside the classic habitable zone, for example on small moons such as Europa. We've also learned that what makes a planet habitable is a matter of great discussion, but at the very least we would expect to need conditions where life has water, an energy source, and where nutrients and elements that it needs to grow and replicate are being replenished. These conditions allow us to assess other planets as abodes for life and also use the criteria for habitability to assess planets orbiting other stars.